What gives certain materials their incredible elasticity and stretch? Imagine a rubber band stretching for beyond its original size and snapping back perfectly every time. What makes some materials able to do this while others break or stay deformed? The secret lies in their molecular structure and how their internal bonds respond to force. At the core, elasticity is a material's ability to return to its original shape after being stretched or deformed. This behavior is driven by forces at the tiny molecular level that resist changes in shape or length. In materials like rubber, elasticity comes from long chains of molecules called polymers. These chains are chemically linked together, forming a network that acts like a bunch of tiny springs. When you stretch the rubber, these chains straighten out, losing some of their natural disorder. This loss of disorder is called a decrease in entropy. Since systems tend to move toward more disorder, there is a natural force that pulls the chains back to their original, coiled state once you let go. This is called entropic elasticity, and it explains why rubber can stretch so much and still bounce back. There are two main molecular mechanisms behind rubber's elasticity. First, when you stretch it gently or moderately, the main restoring force comes from entropy changes as the polymer chains straighten. Second, if you stretch it very far, the chemical bonds themselves start to distort, acting like tiny springs. This bond distortion adds to the restoring force but can cause damage if stretched too far. If the bonds are pushed beyond their elastic limit, they can break, leading to material failure. In metals and ceramics, elasticity depends on how strong the atomic bonds are. Think of bonds as tiny springs holding atoms together. The stiffer these bonds are, the more they resist deformation. Stronger bonds with deeper energy wells mean the material can stretch more without permanent damage. When you apply force, energy is stored in these bonds, and when the force is removed, the bonds snap back, returning the material to its original shape. But if you stretch beyond the elastic limit, the bonds can break, causing cracks or failure. Polymer cross-linking also plays a big role in elasticity. Cross-linking is like tying the chains together with chemical links, making the network more resilient. This process boosts the material's ability to withstand stress and recover from deformation. It's especially important in products like rubber tires or elastic bands, where durability under repeated stretching is needed. At the nanoscale, surface chemistry influences elasticity too. Removing certain chemical groups from a material's surface can make it stiffer, while adding them back can make it more flexible. These tiny changes affect how the material responds to stress and can determine how easily it might fail under pressure. Understanding what makes some materials so elastic helps us design better products. Materials with high elasticity can absorb shocks and recover without cracking. But if they are overstretched or subjected to repeated stress, they can weaken and break. Knowing how molecular bonds and structures behave under force allows engineers to choose the right materials and improve their durability, making sure they last longer and perform better in everyday use.